The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
And welcome back, everybody, to this fun class, L3. Let's get started. The first thing which we will do is to review a bit what we have learned last time, and then we'll go to the next level to start the coupled oscillators. Okay. So last time we have learned a lot on damped-driven oscillators. So as far as the class have been going, actually we only start a single object, and then we introduce more and more force acting on this object. We introduce damping force. We introduced driving force last time. And we see that the system become more and more difficult to understand because of the added component. But after the class last time, I hope that I convinced you that we actually can understand driven oscillators. And there are two very important things we learned last time. The first one is the transient behavior, which is actually a superposition of the homogeneous solution and the steady-state solution. Okay? One very good news is that if you are patient enough, you shake the system continuously, and if you wait long enough, then the homogeneous solution contribution will go away. And what is actually left over is the steady-state solution, which is actually much simpler than what we saw beforehand. It's actually just harmonic oscillation at driving frequency. Also, I hope that you also have learned a very interesting phenomena, which is resonance. When the driving frequency is close to the natural frequency of the system, okay? Then the system apparently like it, okay? Then you would respond with large amplitude and oscillating up and down at the driving frequency. So that we call it resonance. Okay? So this is actually the equation of motion which we have learned last time. You can see it's a theta double dot plus gamma theta dot is a contribution from the drag force. And omega 0 squared theta is actually contribution from the so-called spring force. And finally, that is actually equal to F0 cosine omega dt, the driving force. And as we mentioned in the beginning, if we prepare this system in the underdamped situation, okay, then the full solution is a superposition of the steady-state solution, which is the left-hand side, the red thing pointing to this steady-state solution. There's no free parameter in the steady-state solution, right? So A, the amplitude, is determined by omega d. Delta, which is the phase, is also determined by omega d. There's no free parameter, okay? And in order to make the solution a full solution, we actually have to add in this homogeneous solution back into this again. And basically, you have B and alpha. Those are the free parameter, which can be determined by the given initial conditions. Okay? So if we go ahead and plot some of the example as a function of time, so the y-axis is actually the amplitude, and the x-axis is actually time, and what is actually plotted here is a combination or the superposition of the steady-state solution and the homogeneous solution. And you can see that there are individual components also shown in this slide. You can see the red thing oscillating up and down harmonically is a steady state solution contribution. And also you have the blue curves, which is actually decaying away as a function of time. And you can see that if you add these two curves together, you get something rather complicated. You will get some kind of motion like then the homogeneous solution actually dies out. Then what is actually left over is just the steady state solution harmonic oscillation. And in this case, omega d is actually 10 times larger than the natural frequency. Okay? And there's another example which is actually also very interesting, is that if I make the omega d closer to omega 0, okay, in this case, it's actually omega d equal to 2 times of omega 0. Then you can produce some kind of motion, which is like this. So you have the oscillation, and it stays there for a while, then goes back, and oscillate down, and stay there for a while, then goes back, okay? As you can see from there. The homogeneous solution part and the steady state solution part actually work together and produce this kind of strange behavior, okay? And that's actually just another example. And if you wait long enough, again, what is actually left over is the steady state solution, okay? So what are we going to do today? So today, we are going to investigate what will happen if we try to put together multiple objects and also allow them to talk to each other, okay? So if we have two objects and they don't talk to each other, then they are still like single object. They are still like simple harmonic motion on their own. But if you allow them to talk to each other, this is actually so-called a coupled oscillator, then interesting thing will happen, okay? So in general, coupled systems are super, super complicated, okay? So let me give you one example here. This is actually two pendulums. They are coupled to each other. They are actually connected to each other. One pendulum, the second one is here, okay? And for example, I can actually give it an initial velocity and see what is going to happen. You can see that the resulting motion, okay, remember, we are just talking about two pendulums. They are connected to each other, okay? The resulting motion is super complicated, okay? This is actually one of my favorite demonstrations. You can actually stare at this machine whole time. And you can see that sometimes it does this rotation, sometimes it doesn't do that. And it's almost like a living creature, right? So we are going to solve this system? No, probably not in else. But as I mentioned before, you can always write down the equation of motion, and you can actually solve it by computer, okay? Maybe some of you, the course 6 people can actually try to write the program to solve this thing and to simulate what is going to happen, okay? So let's take a look at this complicated motion again. So you can see that the good news is that there are only two objects, and you can see, okay, look at the green, the orange dot. The orange dot is actually always moving along a semicircle, okay? But if you focus on the yellow dot, okay, the yellow dot is doing all kinds of different things, okay? It's very hard to predict what is going to happen, okay? So what I want to say is those are very interesting examples of coupled system, but they are actually far more complicated than what we thought because they are not actually small oscillation around equilibrium position, okay? So you can see that now if I stop this machine and just perturb it slightly, giving it a small angle displacement, then you can see that now the motion is much more easier to understand. You see, you actually even get one of these questions in your PSAT. Okay, that's the good news. So our job today is to understand what is going to happen to those coupled oscillators. Let me give you a few examples before we start to work on a specific question. The second example I would like to show you is a saw, and you actually connect it to two, actually a ruler, a metal ruler, which is actually connected to two massive objects. Okay, now I can actually give it the initial velocity and see what happens. And you can see that they do talk to each other through this ruler, this metal ruler. Can you see? I hope you can see it. Okay, it's a bit small. But it's very interesting that you can see, originally I'm just actually introducing some displacement in your left-hand side mass. And the left-hand side thing start to move also, right, after a while. There are two more examples which I would like to give you, introduce to you. There are two kinds of pendulums which I prepared here. The first one is there are two pendulums. Okay, they are connected to each other by a spring. Okay, and if I try to actually introduce displacement, I move the both mass slightly and see what is going to happen. And you will see that the motion is still complicated, although if you stare on one of the objects, it looks more like harmonic oscillation, but not quite. For example, this guy is slowing down, and this is actually moving faster. And now the right-hand side guy is actually moving faster. Motion seems to be complicated. Also, you can also look at this one. Those are the two pendulums. Actually, they are connected to each other by this rod here, okay? And of course, you can displace the mass from the equilibrium position. Oh, not going to hit, not hitting each other. So you can displace the mass from each other, and you can see that they do complicated things as a function of time. Okay, how are we going to understand this? And I hope that by the end of this lecture, you are convinced that you can actually solve this really easy, following a fixed procedure, okay? In those examples, we have two objects that are connected to each other, and therefore they talk to each other and produce a coupled motion, okay? Those are coupled oscillators examples. There's another very interesting example, which is called Wilberforce pendulum. Okay, so this is actually a pendulum. Okay, it can actually rotate like this, and it can also move up and down. It's connected to a spring. Okay, the interesting thing is that if I just start with some rotation, okay, you can see that it starts to also oscillate up and down. You see? So initially, I just introduced a rotation. Okay, now it's actually fully rotating, and now it starts to move up and down. And you can see that the energy stored in the pendulum is actually going back and forth between the gravitational and the gravitational potential, between the potential of the spring, and also between the kinetic energy of upside down, up and down motion, and the rotation. Okay, so they are actually doing all those transition all the time, right? So you can see, so initially it's actually just rotating, and then it starts to move up and down. And this this one is also very similar, but now the mass is much more displaced. And if I try to rotate this system without introducing the horizontal direction displacement, it still does this up and down motion like a simple spring mass system. So what causes this kind of motion? That is because when we move this pendulum up and down, we also slightly unwind the spring that actually can generate some kind of torque to this mass and produce rotation behavior. Okay, and you can see that this is actually involving just one single object, but there's a coupling between the rotation and the horizontal direction motion. Okay, so that's actually also a special kind of coupled oscillator. Okay, so after all this, before we get started, I would like to say that what we are going to do is to assume all those things are ideal, okay, without damping force, without driving force. We may introduce that later in the class, but for simplicity, we just stay with just ideal case. Okay, before the math becomes super complicated to solve it in front of you. And also, we can see that all those complicated motion are just illusion, okay? Actually, the reality is that all of those are just superposition of harmonic motions, okay? You will see that by the end of this class. Okay, so that's actually really amazing. Okay, so that's immediately get started. So let's actually take a look at a system together and see if we can actually figure out the motion of this system together. So I have a system with 3 little mass. So there are 3 little mass in this system. They are connected to each other by spring. Those springs are highly idealized springs, and they have spring constant K and the natural length L0. Okay, and they are placed on Earth. Okay, and I carefully designed the lab so that there's no friction between the desk and all those little mass. Okay, so once you get started and look at this system, you can imagine that there can be all kinds of different complicated motions, right? You can actually, for example, just move this mass and put all those the other 2 on hold, and they can oscillate like crazy. They can actually do a very similar kind of motion. There are many, many possibilities. Okay. But if you stare at this system long enough, okay, you will be able to identify spatial kind of motion, which is actually easier to understand. Okay, so what I would like to introduce you is a spatial kind of motion which you can actually identify from the symmetry of this system. Okay. So that is actually so-called normal modes. Okay, so what is actually normal mode? A spatial kind of motion we are trying to identify. That is actually the kind of motion which every part of the system, okay, is oscillating at the same frequency and the same phase. Okay, So that is actually so-called the normal modes, and it's actually the kind of spatial kind of motion which I would like you to identify with me. And we will later realize that those spatial kind of motion, which is easier to understand, actually help us to understand the general motion of the system. You will realize later that the most general motion of the system is actually just a superposition of all the identified normal modes. And we are done because we have a general solution already. Okay, so that's actually a very good news. That actually tells us that we can understand the system systematically and step by step. And then we can actually write the general motion of the system as a superposition of all the normal modes. Okay? So let's get started. So can you guess what are the possible normal modes of this system? So that means each part of the system is oscillating at the same frequency and at the same phase. Can anybody and any one of you guess what can happen? Each part of the system oscillating at the same frequency. Yeah. Very good. So he was saying that now I displace the right-hand side two mass all together by a fixed amount, and also the left-hand side, right, by a fixed amount, and let go. Okay? So that's what you're saying, right? Okay, so the first mode we have identified is like this. So you have left-hand side mass, okay, displaced by delta x, and the right-hand side two mass are also displaced by delta x. Okay, so basically you hold this three little mass and stretch it, okay, by the same, introduce the same amplitude to all those three little mass and let go. Okay, so that is actually one possible mode. And if we do this, then basically what you are going to see is that this is actually roughly equal to this system. They are connected to each other by two springs, and the right-hand side part of the system, since both masses are oscillating at the same amplitude at the same phase, they look like as if they are just one single mass with mass equal to 2m. Okay? And if we introduce a displacement of delta x, then what is going to happen is that if I take a look at the mass, the left-hand side mass, and the force acting on this mass, the force will be equal to minus 2k times 2 delta x, right? Because that's actually the amount of stretch you introduce to this spring, right? Okay, and that will give you minus 4k delta x, okay? And we have already solved this kind of problem in the first lecture, right? So therefore, you can actually immediately identify omega, okay? In this case, omega A squared will be equal to 4k divided by 2m, right? This is actually the effective spring constant, and this is actually the mass, right? Okay, so that is actually the frequency of mode A. Okay, can you identify a second kind of motion which does that? So in this case, what is going to happen is that the three mass will, okay, this 1, 2, and 3. The three mass will do will oscillate as a function of time like this, with angular frequency of square root of 4k over 2n. What is actually a second possible motion? Yes.
One of the small masses being stretched and the second small mass being
compressed.
Compressed with the same.
Very good. I'm very lucky that I'm in front of such a smart crowd today. And we have successfully identified the second mode, mode B. Okay, so what is going to happen is that the left-hand side mass is not moving, right? And you compress the upper one slightly, and you actually stretch the lower one, the lower little mass, to the opposite direction, okay? The displacement is delta x, and the displacement of the second mass is delta x, okay? So what is going to happen? What is going to happen is that the left-hand side mass will not move at all, right? Because the force, the spring force is going, acting on this mass is going to cancel, right? Okay? And apparently these two little mass is going to be doing harmonic motion, okay? But they are actually, since this left-hand side mass is actually not moving, it's as if this is a wall, and this was a single spring, K, and it's actually connected to a little mass. And it actually got displaced by delta x. Okay, so what will happen is that this mass will experience a spring force, which is F equal to minus K delta x. Therefore, we can actually immediately identify omega b squared will be equal to K over m. Okay? So you can actually see that we have identified two kinds of modes, which every part of the system is oscillating at the same frequency and at the same phase. Everybody agree? No, not everybody agree. Look at this guy. This guy is not moving, right? How could this be? This is actually not a normal mole, right? Isn't it? Okay, I hope that wake you up a bit. I can be very tricky here. I can say that this mass is actually also oscillating, but with what amplitude? Zero amplitude, right? So the conclusion is that, everybody is actually oscillating at the same frequency, but this guy is with zero amplitude, okay? Yes.
Are they oscillating at the same phase as well?
Yeah. Oh, very good question. So another objection I received, right? So life is hard for me today. Hey, this guy is actually oscillating out of phase, right? These two guys are out of phase, right? But I can argue that the amplitude of the first mass is actually minus, actually have a minus sign compared to the second mass, okay? Then they are, again, in phase, okay? Okay, so very good. I like those questions. And I hope that I have convinced you that everybody is oscillating, although you cannot see it because the amplitude is small, it's zero. And they are all oscillating at the same phase. Okay? Yes?
How come there's only one mass?
Oh, the right-hand side? Oh, yeah. That is because the left-hand side mass, the 2m1, is actually not moving, right? Because there are two spring force. One is actually pushing the mass. The other one is pulling the mass, okay? And they cancel perfectly, okay? Therefore, it's as if those two guys are not, they don't find each other actually, and then it's like okay, they are just two mass connected to a wall alone, and you can actually now identify what is actually their frequency. Okay, very good. Okay, so we made a lot of progress from the discussion, and now I would like to ask you for help. What is actually the third oscillation? Yes.
There is no third normal mode.
There's no third normal mode.
There is no third normal mode because we are restricted to one dimension. And I cannot imagine another motion that will not displace the center of mass.
Yeah, very good. That's very good. So on the other hand, you can also say, I also take the center of mass motion as one of the normal mode. Yeah, I think that's also fair, okay, to do that. Okay, it's very good observation. You can see that the whole system can move simultaneously, right? And they are also I can also argue that they are oscillating at the same frequency, at the same phase, because they are all moving together. So this is the 2m connected to S1, S2, okay? All of them are moving at the same direction, okay? So now I can calculate the force. What is the force? F is 0. Therefore, omega c is 0, okay? So you can actually take the small limit of omega, okay? So of course I can pretend that those mass are connected to a really, really small spring to the wall with a spring constant K prime, and I have K prime goes to 0, and they are actually going to oscillate with omega c goes to 0, okay? So in this case, the amplitude is going to increase forever, right? Because you have basically A sine omega ct, right? And this is actually roughly A omega c t. And this is actually just Vt, right? So what I want to argue is that this is actually also oscillation, but with angular frequency 0. And the general motion can be written as Vt times c, for example, some constant. Okay? Any questions? So what I'm going to do next may amaze you. Very good. So we have identified 3 different kinds of modes. We have mode A, which is actually with omega A squared equal to omega A squared. Where's omega A squared? There. It's 4k over 2m. And also, the motion is like this. x1 equal to A cosine omega A t plus phi A. x2 is equal to A minus A, actually, because they are actually having a different sign, right? So if the motion is actually in the left-hand side direction, then the 2 mass is actually oscillating in the opposite direction, right? So therefore, I get the minus sign in front of A, okay? Cosine omega A t plus phi A. x3 will be also equal to minus A cosine omega A t plus phi A. Of course, I need to define what is x1, x2, and 3, right? That's actually why most of you got super confused. Okay, so the x1, what I mean is that it's the displacement of the mass 2n I call it x1. The displacement of the upper mass, the upper little mass, I call it x2. And finally, the displacement of the third mass, I call it x3, right? Therefore, you can see that mode A, you have this kind of motion. Okay, the amplitude of the first mass is A. Therefore, if I define that to be A, then the second and third one, the amplitude will be defined as minus A. And you can see that all of them are oscillating at fixed angular frequency, omega A, omega A, omega A, and also fixed phase, phi A, phi A, phi A. Okay? Of course, we can also write down what we get for mode B, right? For mode B, the left-hand side mass is not moving, stay put, and the other two masses are oscillating at the frequency of omega B, and the amplitude, they actually differ by a minus sign, okay? Omega B squared is equal to K over M from that logical argument. And then actually we get x1 equal to 0 times cosine omega bt plus phi b. x2, I get b cosine omega bt plus phi b. x3, I get minus b cosine omega bt plus phi b. Any questions here? Okay. Finally, mode C. Okay. All the mass x1 is equal to x2 is equal to x3 is equal to C plus Vt. Okay. So you can see that we have identified 3 modes: mode A, mode B, and the mode C. Okay, and there are 3 angular frequencies which we identified for all those normal modes. Okay, omega A, omega B, and omega C. Okay, and you can see that we also identified how many free parameters. 1 free parameter, 2, 3, 4, 5, and 6. So if you are careful, you write down the equation of motion of this system. You will have 3 coupled differential equations. And those are second-order differential equations. If you have 3 variables, 3 second-order differential equations. If you manage it magically with the help from a computer or from math department people, right? How many pre-parameters will you expect in your general solution? Can anybody tell me how many? I have 3 second-order differential equations. Yes? 6, right? So look at what we have done. We identified already 1, 2, 3 normal modes, right? And there are 1, 2, 3, 4, 5, 6 free parameters. That tells me I'm done. Right? I'm done, because what is actually the general solution? The general solution is just a superposition of mode A, mode B, and the mode C. You have 6 free parameters to be determined by 6 initial conditions, which I have to tell you what are those initial conditions, okay? So isn't this amazing to you? I didn't actually even solve the differential equation, and I already get the solution, okay? And you can see another lesson we learned from here is that although you can imagine that the motion of this system can be super complicated, this whole thing can do this, all the crazy things all over the place, and the central mass can move, as you said. But the result is actually very easy to understand. It's just 3 kinds of motion, the displacement, and 2 kinds of simple harmonic motion. We add them together, and then you will get the general description of that system, okay? So everything is so nice, right? We understand the motion of that system, but in general, life is very hard, okay? For example, now I do something crazy here. I change this 2 to 3. What is actually the normal mode? Can anybody tell me? It becomes very, very difficult because there's no general symmetry of that kind of system, right? So we are in trouble, okay? One of the mode may be still there, which is actually mode B, but the other modes are harder to actually guess, right? So you can see that actually already brings you a lot of trouble. And you can see that I can now couple not just 2 objects, I can couple 3 objects, 4 objects, 5 objects, 10 objects. Maybe I will put that in your P set and see what happens. And you can see that this becomes very difficult to manage, right? So what I'm going to do in the rest of this lecture is to introduce you a method which you can follow in general to actually solve the equation and get the normal mode frequencies and normal modes. Okay, so we will take a 4-minute break, and we will come back at 12:20. So if you have any questions, let me know. So what we are going to do in the following exercise is to actually try to understand a general strategy to solve the normal mode frequencies and the normal mode amplitudes, okay? So that actually you can apply this technique to all kinds of different systems, okay? So what I'm going to do today is to take this 3-mass system, and of course, as usual, I try to actually define what is the coordinate system. The coordinate system I'm going to use is x1, x2, and x3, describing the displacement of all those mass from equilibrium position. And the equilibrium means that there's no stretch on the spring, okay? The spring is actually unstretched. It's actually at their own natural length, L0, okay? So once I define that, I can do a force diagram analysis. And so that starts from the left-hand side, mass with mass equal to 2m, okay? I can write down the equation of motion, 2m x1 double dot, okay? And this is going to be equal to k x2 minus x1 plus k x3 minus x1, okay? So there are 2 spring forces, right, acting on this mass, the left-hand side mass. The first one is the upper spring. The second one is coming from the lower one, okay? And you can see that both of them are proportional to spring constant k, and also proportional to the relative displacement. And you can see that the 2 relative displacement, which is actually the amount of stretch to the spring, okay? It's actually x2 minus x1 and x3 minus x1, okay? Am I going too fast? Okay, everybody is following. And you can actually check the sign, right? So you may not be sure. Maybe this is actually x1 minus x2, right? But you can check that, because if you increase x1, what is going to happen? This term will become more negative, right? More negative in this coordinate system is pointing to the left-hand side. So that makes sense, right? Because if I move this mass to the right-hand side, then I am compressing the springs, right? Therefore, they are pushing it back. Therefore, this is actually the correct sign, x2 minus x1, okay? The same thing also apply to the second spring force, okay? So that's actually a way I double check if I make a mistake, okay? All right, now this is actually the first equation of motion. Then I can now also work on a second mass. Now I focus on mass number 2. The displacement is x2. Therefore, the left-hand side of Newton's law is mx2 double dot, okay? And that is actually equal to the spring force, right? The spring force, there's only one force one spring force actually acting on the mass. Therefore, what I'm going to get is k x1 minus x2. Okay, everybody is following? Okay, you can actually check the sign carefully also. And finally, I have the third mass, very similar to the mass number 2. I can write down the equation of motion, which is actually k x1 minus x3, right? So that is actually my coupled second-order differential equations. There are 3 equations, and all of them are second-order equations, okay? So this looks a bit messy, right? So what I'm going to do, there's no magic. I'm just collecting all the terms belonging to x1 and put them together. All the terms belonging to x2, put them all together, and just rearrange things, okay? So no magic. So I copy this thing left-hand side, 2m x1 double dot, and that will be equal to minus 2k x1 plus, I collect all the terms related to x2, plus k x2, there's only one term here, right? Then plus k x3. Okay, I'm just trying to organize my equation, okay? Okay, so you can see that I collect all the terms related to x1 to here, minus k, I get minus 2k. And the plus k for the x2, plus k for the x3. And now I can also do that for mx2 double dot. That will be equal to k x1 minus k x2 plus 0 x3, just for completeness, okay? I can also do the same thing for the third mass, nx3 double dot. This is equal to k x1 plus 0 x2, right? There's no dependence on x2, right? Because x1 and x2, x3 and x2 are not talking to each other directly, right? Finally, I have the third term, which is minus k x3. Okay, so now our job is actually to solve those coupled equations, okay? Of course, you have the freedom, if you know how to solve it yourself, you can already go ahead and solve it. But what I'm going to do here is to introduce a technique which can be useful for you and make it easier to follow. It's a fixed procedure, okay? So what I can do is the following. I can write everything in the form of matrix. How many of you heard the matrix for the first time? 1, 2, okay, 3, 4, okay, only 4, right? But if you are not very familiar with matrix, let me know, and I can help you, let the TA know. And also, there's a section in the textbooks which I actually posted on in the announcement, which is actually very helpful to understand the matrix. But sorry to this for students, we are going to use that, and maybe you already learned how it works from here. Okay? So one trick which we will use in this class is to convert everything into matrix format. Okay? So what I'm going to do is to write everything in terms N, capital X, capital N, capital X, double dot, equal to minus capital K, capital X. Capital M, capital X, and capital K, those are all metrics, okay? Because I write this thing really carefully, therefore we can already immediately identify what will be M, capital M and capital X, and the K, okay? So I can write down immediately N will be equal to 2M, 0, 0, 0, and 0, 0, 0, N, right? Because there's only one, in each line you only have one term, right? X1 double dot, X2 double dot, X3 double dot, okay? And also you can write down what would be the X. This is actually a vector. X will be equal to X1, X2, X3, okay? Finally, you have the K. How do I read off K? Okay, care for this minus sign here, right? Because I would like to make this matrix equation as if it is actually describing a simple harmonic motion of a one-dimensional system, right? So it looks the same, but they are different because those are actually metrics, okay? But therefore, I have, in my convention, I have this minus sign there, okay? Therefore, when you read off the K, you have to be careful, okay? So what is actually K? K is actually equal to 2K, right? You have the minus 2K here in front of X1, but because I have a minus sign there, therefore this one is actually taken out, okay? So you have 2K there, okay? Then you have minus K, okay? Minus K, K, 0, minus K, plus K, 0, right? And finally, you can also finish the last row. You get minus K, 0, K, right? K become minus K become K, okay? So we have read off all those metrics successfully, right? So you may ask, what do they mean, right? What do they get the meaning, right? M, K, X, what are those? Okay, M, the capital M matrix, tells you the mass distribution inside the system. So that's the meaning of this matrix, okay? X is actually a vector, which actually tells you the position of individual components in the system, okay? Finally, what is K? K is telling you how each component in the system talk to the other components, okay? So K is actually telling you the communication inside the system, okay? So now we understand a bit what is going on. And as usual, I will go to the complex notation. Okay, so I have xj, the small xj are the position of the mass, right? x1, x2, and x3. Xj will be a real part of small zj. Okay, small xj equal to a real part of zj. Okay, therefore, I can now write everything in terms of matrix again. So now I can write the solution to be z. The capital Z is a matrix. Okay, exponential I omega t plus phi. This is the solution I have. A1, A2, and A3. Those are the amplitude A of the first mass, amplitude of second mass, amplitude of the third mass, okay, in the normal mode, right? And all of those are oscillating at the same frequency, omega, at the same phase, phi. Does that actually tell you something which we actually learned before? Oh, that's the definition of the normal mode. I'm using the definition of the normal mode. Every part of the system is oscillating at the same frequency and the same phase, and we use that to construct my solution, which is actually the complex version is actually exponential I omega t plus phi, oscillating at the same frequency, oscillating at the same phase, and those are the amplitude, which I will solve it later. Okay? Any questions? And I hope I am not going too fast. Okay? If everybody can follow, now I can go ahead and solve the equation in the matrix format. Okay? So now I go to the complex notation, right? So the equation nx equal to minus kx, nx double dot equal to minus kx become nz double dot equal to minus kz. Right? And also I can immediately get z double dot will be equal to minus omega square z, right? Because each time I actually do a differentiation, I actually get an I omega out of the exponential function, right? And I cannot kill that exponential function, so it's still there, right? Therefore, I get minus omega square in front of z. I hope that doesn't surprise you, okay? So that's very nice and very good news. That means I can actually replace this z double prime with minus omega square z. Then I get minus n omega square z, and this is equal to minus kz. And I can cancel the minus sign. That becomes something like this. Okay? So I can now actually cancel the exponential I omega t plus phi, right? Because I have a z in the left-hand side, and exponential I omega t plus phi is just a number, right? So therefore, I can cancel it, okay? So what is going to happen if I do that? Basically, what I'm going to get is I get n omega square a equal to ka. Okay, I'm trying to go really extremely slowly because this is the first time we go through matrix. Okay, so now you have this expression. Left-hand side is a matrix n times some constant omega square. I can actually get the omega square in front of it because this is actually just a number. Okay, a is actually a vector, which is A1, A2, and 3. Okay, also a matrix. K is actually how the individual components talk to each other, right? So that's there times A. Okay. Now I would like to move everything to the right-hand side, all the matrix in front of A to the right-hand side. Then I multiply both sides by n minus 1. Okay, so I multiply n minus 1 to the whole equation. Okay, n minus 1, what is actually the n minus 1 is actually the definition is that the inverse of n is called n minus 1. N minus 1 times n is equal to I, which is actually 1, 1, 1. Okay, therefore, if I do this thing, then I will get omega square. N minus 1 times n become I, right? Becomes this unit matrix A, and this is equal to n minus 1 k A. Okay, and to be careful, I multiply n minus 1, the inverse of m, from the left-hand side. Okay, that matters. Okay. So now I can actually move everything to the same side. Okay, actually I move the left-hand side, turn to the right-hand side. Therefore, I get n minus 1k minus omega square I. Okay, This is actually, those are all metrics, okay? Times A, this is equal to 0. Any questions? Okay. So a lot of manipulation, but if you think about it, if you are following me, you'll see that, all those steps are exactly identical to what we have been doing for a single harmonic oscillator, right? It looks pretty familiar to you. But the difference is that now we are actually dealing with metrics. Yes?
What is A?
Oh, A. Oh, sorry. A is actually this guy. I define it to be A, and that means Z will be exponential I omega t plus phi times A. Okay, I didn't actually write it explicitly, but that's actually what I mean. Okay. Any more questions? Yes.
So this whole thing is for mode A, right?
Can you repeat that?
This whole process is for mode A, right?
Yeah, so this whole process actually for, not really for mode A, so that A may be confusing, but it's actually for, but in general, if I have a solution and I assume that the amplitude can be described by a matrix, okay? So it's in general, and you will see that we can actually derive the angular frequency of mode A, mode B, and mode C afterward, okay? I hope that answers your question. Okay, so you see, for in general, so what I have been doing is that now, actually, all those things are equivalent to the original equation of motion. What I'm doing is purely cosmetic. You see, make it beautiful, right? Right? So all those things. This thing is exactly the equivalent to that thing, up to there. Up to mx double dot equal to minus kx. Cosmetics. Beautiful, okay? Looks, I like it, okay. All right? Then what I have been doing is that now I introduce, using the definition of normal mode, I guess the solution will have this functional form. Z equals to exponential I omega t plus phi. Everybody oscillating at the same frequency, the same phase, frequency omega, phase phi, but everybody can have different amplitude, right? You can see from this example of normal modes, you see, they can have different amplitude, right? Okay, the amplitude is what? I don't know yet, but we will figure that out, okay? Then that's my assumption, the definition of normal mode, then I plug in to the equation of motion. Then this is actually what we are doing to simplify the equation of motion, okay? There's no magic here, okay? If I plug in the definition of normal mode to that equation, this is actually going to bring you to this equation, okay? Matrix equation. Okay? So if you have learned matrix before, you have something, some matrix, times A, okay? This is equal to 0, okay? A is actually not 0, right? I hope. If it's 0, then the whole system is not moving, then it's not fun, right? Okay, so if A is not 0, then this thing should be, this thing times A should make this equation equal to 0, right? So what is actually the required condition? Okay, I got stuck, and of course, again, my friend from math department come to save me. That means if this thing, okay, have solution, this equation have solution, that means the determinant of n minus 1k minus omega squared I has to be equal to 0. Okay, so that is actually the condition for this equation to satisfy this to be equal to 0. Okay, and and just to make sure that I don't know what is actually the angular frequency omega yet, I don't know what is actually the phi yet. Okay, actually we can actually solve the angular frequency omega. Okay, so now what we actually turn everything around, and basically now using this normal mode definition and some mathematical manipulation, the condition we need for this equation to satisfy equal to 0 is determinant n minus 1k minus omega squared I. Okay? I can write down n minus 1k minus omega squared I explicitly, okay? Just to help you with mathematics. N minus 1k is actually equal to 1 over 2m, 0, 0, 0, 1 over 2m, 0, 0, 0, 1 over m. It's just the inverse matrix of the M matrix. Okay? Therefore, now I can actually write down the explicit expression of n minus 1k minus omega squared I. Okay, this will be equal to k over m minus omega squared. Okay, minus k over 2m minus k over 2m minus k over n, k over n minus omega squared, 0. I will write down all the elements first, then I will explain you how I actually arrive the expression. Okay, so this is n minus 1k. The definition of n minus 1 is there, and the definition of k is in the upper right corner of the blackboard. Okay, therefore, if you multiply n minus 1k, basically the first row, the first column will get. Okay, wait a second. Did I make a mistake? No. Okay. So basically, what you actually arrive is k over n, k over n, k over n, and also the minus k over 2n for the rest of the part of the matrix. And the minus omega squared I actually will give you the diagonal component. Okay? Yes?
Why do you have to take the determinant and set it equal to 0 instead of just setting that equal to 0?
That is actually, this is actually matrix, right? So this is a matrix. So a matrix times A will be equal to 0. The general condition for that to be satisfied is actually more general. It's actually the determinant of this matrix equal to 0. Okay? Because this is actually multiplied by some vector A. Okay? Okay, so I think there are mathematical manipulation. Basically, you just collect the term and then calculate the n minus 1k first, and the minus omega squared I will give you all the off-diagonal term have a minus omega squared there, okay? And that is actually the matrix. And of course, I can actually calculate the determinant. So if I calculate the determinant, then basically I get this times that, right? So basically what you get is k over n minus omega squared times k over n minus omega squared times k over n minus omega squared, right? So these are all diagonal term. And the minus 1 over 2 k squared over n squared, k squared over n squared, k over n, sorry, minus omega squared. Okay, So that is actually this off-diagonal term. This times that. Okay, you give you the second term, and the third one which survive because of those zeros, right? Many terms are actually equal to 0, and the third time which actually is not 0 is again minus 1/2 k squared over n squared, k over n minus omega squared. And this is actually equal to 0 because the determinant of this matrix is equal to 0, okay? Everybody following? A little bit of math because I have been doing something very challenging. I'm solving a three-dimensional, actually a 3x3 matrix problem in front of you, right? So the math can get a bit complicated, but next time I think we are going to go through a second order 2x2 matrix, and I think that will be slightly easier. But the general approach is the same, okay? So basically you calculate n minus 1k minus omega squared, then you get what is actually inside, all the content inside this matrix. Then you will calculate the determinant, okay? And basically you can solve this equation, right? Now I can actually define omega 0 squared to be k over n, and I can actually make this expression much simpler. Then basically what you are getting is omega 0 squared minus omega squared to the third minus 1/2 omega 0 to the 4 omega 0 squared minus omega squared minus 1/2 omega 0 to the 4 omega 0 to the square minus omega squared. And this is equal to 0, okay? And actually you can factorize out the common components. Then basically what you are going to get is you can actually rewrite this thing to be omega 0 squared minus omega squared, right? Because all of them have actually omega squared, and omega squared minus 2 omega 0 squared. Now this is equal to 0, okay? So I am skipping a lot of steps from this one to that one, but in general, actually you can solve the third order equation. And actually I can first actually combine all those terms together, right? And then I factorize out the common components. Then basically what you are going to arrive is something like this, okay? A lot of math here, but we are close to the end, right? So you can see now what are the possible solutions of omega. That is actually the omega unknown angular frequency we are trying to figure out. You can see that, there are 3 possible omegas can make this equation equal to 0, right? The first one is omega equal to omega 0. The second one is square root of omega 0, right? Coming from this expression, right? Omega squared minus 2 omega 0 squared. If omega equal to square root of omega 0, this will be equal to 0, and that will give you the whole expression equal to 0. Then finally, I take this term, then you get 0, right? Omega squared, if omega is equal to 0, then the whole expression is 0, okay? I have defined omega 0 squared to be equal to k over m, right? Therefore, I can conclude that omega squared is equal to k over m, okay? 2k over m and 0. Look at what we have done. A lot of mathematics, but in the end, after you solve the eigenvalue problem or the determinant equal to 0 problem, you arrive that there are only 3 possible values of omega which can make the determinant of n minus 1k minus omega squared I equal to 0. What are the 3? K over m, 2k over m, and 0. if we look at this value and we say, this is actually what we actually argued before, right? Omega A squared is equal to 4k over 2m. It's 2k over m. Wow, we got it. Okay? The second one is, we think about really scratching my head and understand this system. And, the second identified normal mode is having omega b equal to square equal to k over m. I got it also here, magically, right? After all those magics, right? And finally, the third one, the math also know physics. You also predict that there's one mode which have an oscillation frequency of 0. Isn't that amazing to you? But that also gives us a sense of safety, right? Because if I can now add 10 pendulum or 10 coupled system to your homework, and you will be able to solve it, right? Okay, so very good. So this example seems to be complicated, but what I want to say, I have 1 minute left, is that what we have been doing is to write the equation of motion based on force diagram. Then I convert that to a matrix format, mx double dot equal to minus kx. Then I follow the whole procedure, solve the eigenvalue problem. Then I will be able to figure out what are the possible omega value, okay, which can actually satisfy and this eigenvalue problem or this determinant n minus 1k minus omega square I equal to 0 problem. And after solving all those, you will be able to solve the corresponding so-called normal mode frequencies. You can actually solve it. And of course, you can plug those normal mode frequency back in, then you will be able to derive the relative amplitude A1, A2, and A3, okay? So what have we learned today? We have learned how to predict the motion of coupled oscillator, okay? That's really cool. And the next time, we are going to learn spatial kind of motion in coupled oscillator, which is the beat phenomena, and also what will happen if I start to drive the coupled oscillators. So I will be here if you have any questions about the lecture. Thank you very much.